All right, welcome to our final lesson of AP Calculus AB, our last day of learning new material, and then it's all review from here on out. Today is Monday, March 16th, 2020, and it is our last day before we are on isolation for COVID-19. Yeah, so like people watching in 3 years be like, oh, that happened? That's in our history book. Yes. So, I know, right? Our objective today, Arrow, is to do what?
Find volumes of revolution when rotated around axes that are not the x nor y axis.
There it is, yeah. So I'm rotating around a line that's up here, or over there, or this way. It's not on the axis. So let's talk about the one that is revolved around the axis, which I'm going to call basic, and then the one that are not, today's lesson, the advanced. So let's go ahead and draw a shape. And your shape should be relatively similar to mine, just to make it easier. I'm going to do a blue function that looks like that, a red function that looks like that, and they intersect each other there and there. So I'll call these points here. That x-coordinate is going to be called A. This x-coordinate over here is going to be called B. And I can make my B look slightly neater. Okay, and then you kind of are going to copy-paste that onto your advanced slide. And I'm thinking, do I want to make mine go down a little bit? Probably. So if you drew yours too far up, I apologize. It probably needs to be down right about there. That makes more sense. Then kind of copy-paste that onto your next one. So you start out with your same image. I'll let you guys catch up. I guess I should be labeling these things too. Let's call our blue function f of x, and f of x. Now I feel silly because I could have copy-pasted all of this. And our lower function g of x, we might want to call that g of x out to the side because we're going to be using this area to revolve, and you're going to be writing here. So I'm going to write g of x off to the side and say that red function is g of x. I think that's all we need to do before we start deciding where to rotate around. So again, rotate and revolve, those are the kind of key words that mean that we're going to be doing some sort of cross sections that are circles. So I forgot to mention in our last notes, I should be mentioning it now. I'll fix it for next year. If you see the word rotate, or if you see the word revolve, that's 11-4 and 11-5 for the notes. That means our volume is going to have pi. Volume, I'll just say has pi. Has pi. If you see a square cross section, a triangle cross section, you're not going to be seeing pi. I guess you might be seeing pi if you do a semi-circle, but that's kind of a weird, it's not that weird, but it's not that often that the AP test has those. A lot of people get confused on like the a squared or the top squared and bottom squared. I shouldn't touch my face. The top squared and bottom squared, does that have pi in it or not? Do you see any circle in it? These are going to have circle because we're going to rotate them. So this one, I'm going to rotate it around the x-axis. So the way that we annotate that is we put a little arrow that goes around the x-axis. And we've seen that before. But the advanced one is going to have its axis of rotation, I don't know, let's put it a little bit lower down here. Axis of rotation, maybe a little bit higher than that, right about there. We'll say like y equals -2 or something like that. So its axis of rotation will do a little arrow, or Claire, sorry. A little Claire goes around that axis right there. And of course, I could be rotating this around the, like an x equals function. It doesn't have to be a line like that. I could be rotating it around a line like that. It could be perpendicular to the one I'm currently doing. So just know it could be either way, just be wary. All right. How does that look in our notes? Well, I'm gonna do my best attempt to sketch this guy. So if I'm here, then I'm gonna jump over right about there. So I'm gonna do a line that looks like that, a curve, and that means I have a curve that's down here like that. And then I'm gonna have to draw this same shape upside down. So here's the red g of x that's rotated down here. Here's the blue f of x that's rotated right there. And I'll try to make this three-dimensional. So there's the shape, and I can do maybe a dashed dotted line on the inside. So this is the volume, and it's really hard to visualize on paper, and that's why luckily we have Kaylin and Sophia's shapes like these. You always want to be thinking about it as, yes, you have one starting shape, and then you are rotating that shape until there are an infinite number of that shapes around that axis, and you have to do your best to visualize what that's going to look like. All right, and then very similarly, we're going to do the same thing, or almost the same thing over here. So if I'm that distance, I'm going to do that same distance down here. So my dot's going to be right about there. So it's a lot lower now. And It's going to go through here once and dotted line on the inside right there. And then I'll have a point down here, and it's going to be a much bigger arc this time right here. And you might be thinking, okay, so they're farther apart. What does that mean in terms of my answer that I should be getting? And the answer to that question is that volume should be bigger. It's a bigger shape, right? So we can kind of check our work. If we did both of these at the same time, do we get a bigger or smaller answer when I'm doing different axes of revolution? All right, I'm going to pause here. This is my time to give you, like, really imagine what these shapes look like. They don't have any base in them, so I can put my hand all the way through it. They're curved on the inside and on the outside. What would it feel like if I actually touched this 3D object? Like, can you physically see what that would look like in your mind's eye?
It's just that we make this with a 3D printer, so we show next.
Oh my god, that is such a good idea. If I do the same notes every year, I should just totally make.
Yeah, that'd be good.
And it's, yeah, there's a lot of people that already have those scripts ready to go. All right, so what do the cross sections look like? So this one has a smaller cross section. Again, I'm gonna have a small circle on the inside. So let me do a small circle. Ooh, that's not a circle. Small circle on the inside. Shwink. Let's go like that. This one's gonna be a slightly bigger small circle. And then I'm gonna need a different color. So my f of x is slightly, come on now, I changed to blue. There it goes. That's gonna be slightly bigger. So that's what my cross section is gonna look like there. And then my cross section over here is gonna look like that. But the main thing is that the distance in between my red and blue is the same distance. I mean, the shape up here hasn't been changed. It's still the same distance here, the same distance here. It's just now my radius is bigger for both of them by the same amount. By how much, you might ask? Well, by the amount from the x-axis to this new axis of rotation. So again, if you remember all the way back from Friday in notes 11-4, the way that we found the area was we did big circle area minus small circle area. So can you guys remind me what the formula is for that small one? Integral from a to b, right?
A to b.
There's a pi that came out front. What else was there? I'll do square bracket.
F of x minus g of x.
F of x squared or f of x minus g of x quantity squared?
Quantity squared.
That's a square cross section, so be careful. Because you want to be thinking about this. This is pi r squared. This is pi r squared. Each of them is squared individually. So this is f of x squared.
Minus g of x squared.
Exactly, yeah. Minus the g of x quantity squared. And there's our formula, and that dx. And then dx is our thickness dx. And again, if you want to add a third dimension onto this, it's no longer a cross section if you do that. Well, I guess if it's a cross section that has width, anyway, you can kind of pretend to have some thickness there. That thickness of this slice is going to be a d of x. I'm going to leave it off for now, just to make the notes simpler. So there's our old formula. But now our formula has to be bigger. So what's our new formula going to look like? Well, let's kind of rediscover it. So if I have a radius, let's go here and switch to my radius. So I have a radius, let's do there, versus a radius out here, looks like this. So these two radii, what are the lengths of those radii? What is the distance between f of x, and not x, but f of x and this function? We'll call it y is equal to k. I think we use k in here. I'm again using like some really old notes, so it's hard for me to look. I'm just going to call this y is equal to k. I don't know what height this is. I'm just going to call it k. Maybe you can think of k today as -2 or -1 or -3 or something like that. Something negative because it's below the x-axis.
Wait, which radius are we finding? The inner one?
I want to try to find either the red or the blue. Let's start with the red.
Isn't it the absolute? No, the height of g of x plus the absolute value of k.
Yeah, so that's a not quite correct way of thinking of it, because if I add them, if I had k up here, if I add this height to this height, I should be getting a height that's up there, which is not correct. It's like a good guess, but not quite. What is this distance going to be? It definitely has to have some g of x in there. I don't know if I'm adding or subtracting that g of x. And this formula is pretty simple. There's no absolute values in it.
We'll go with g of x minus k.
There it is, g of x minus k. Why minus k, Mr. Snell? If I subtract k, won't that make it smaller? Well, check it out. If this k is a negative value, then I'm doing a positive minus a negative, which is really adding. And if I just subtract them, if I had something that was positive, g of x minus something positive is going to make it smaller, which again, this height is smaller than that height. So there's your formula. That's really just g of x minus k. And then similarly, stego, this is going to be f of x minus k. Done. So those are our new radii. So I just I plug them into our formula. That is the radius. That entire radius now needs to be squared in our formula. So I'm going to label this one as the old formula. That's not how you spell old.
Odd.
This is the old formula. Our new formula, I don't know if I have enough room to fit it in here. I'm going to come down here just in case. It's the integral, again, between a and b still. I still have a pi that's factored out of it. I don't want to rederive the whole thing because we want some time to actually do some homework today. It's going to be the outer minus the inner. So the outer still are blue. F of x minus k. That quantity, that is the radius, so that quantity is going to be squared. That is a radius squared. And then I'm going to subtract that from the inner. So minus the inner, I should do black for the minus sign, minus the inner. Inner is g of x in this case, g of x minus k. Quantity squared. And that whole thing times the thickness d of x. And please label this thing. Remember that blue is our outer and red is our inner. All right, so then the question becomes, Mr. Sindel, how am I supposed to memorize both of these formulas? Well, really, ignore that old formula. Just memorize the new formula, right? If k is the x-axis, then k is 0. And then it becomes the exact same formula as this one. So there's really only one formula, and it's the one that we just learned today. So I kind of lied to you guys last Friday. But there's the one formula that you need to know whenever you revolve a shape around any sort of line. It can be an axis, an x-axis, a y-axis. It could be x equals 3, y equals negative 10. Cool beans. I think that's it. We don't have a backside, right? Yep, okay. Can you guys give me a fist five? How well do you think you can do our new advanced volumes of Revolution? I'm seeing a 3, a 4, and a 4.